So now we're going 120 years back in time. You know the basic thing, but the group theory is much smarter than that. So the basic thing is if you have some matrix, so I have 6 matrices here, I can diagonalize any one of them. I can find a transformation that finds its eigenvalues, eigenvectors. And eventually, I could stick these permutation matrices to a computer, I could run MATLAB and I'll get the results. But the formula is much more beautiful and it works for all finite groups. And the formula says that if I want to find one of these guys, lambda of alpha, like plus and minus, but now the labels run over irreducible representations, I can obtain it from the original function by a projection operator. I take my original function, I multiply it by something that you've seen in Fourier analysis. There it was called the Fourier coefficient, and this was, in Fourier analysis, what happens is that all representations are dimensional, and this label is actually momentum, k, that you know. So if you're on a finite circle of n elements, you will get a diagonal thing after Fourier, but Frobenius generalized this to any finite group, where this is both dimension and the degeneracy of irreducible representation alpha. So in the example that I'll work out next, which will be the 3-disk example, dihedral group D3 or C3V or S3 permutation on 3 elements. So group of 6 elements, order. For finite groups, the number of elements is called order. We'll be able to bring a 6x6 matrix into the form of 1 by 1, 1 by 1, 2 by 2, and a copy of the same representation. It shows up twice. So that's the dimension of it. This H is the one that you know. So that's the operation that brings you, you start at X and now you look whether you land in the tile which is fundamental tile moved by this operation someplace else. And you give it this weight, which is called character. This character is the trace of this group operation. For example, character of identity is dimension or order of the group, because it's 1, 1, 1 any place. But the character of that flip was 0, because it was a matrix that had nothing on the diagonal. So it looks very fancy, but for discrete groups it's not all that fancy. It's some integers. And the sum goes over all group operations. So now remember how we derived our trace formulas and spectral formulas. For trace formulas, we took a trace, and now we see how this trace is going to work. It's going to be trace computed of fundamental domain. That trace will only pick up elements if this H is the thing that brings me back to fundamental domain. We'll only pick up contributions from relative periodic orbits, orbits which land in some other tile exactly the same position. So when I bring them back, they become periodic on the elementary cell. So we now see that the trace will be the sum of traces. Remember, we need traces to compute our stuff. So, trace is a sum of traces of these guys. So trace of our original operator. Right, again, it's you start someplace and you return exactly to the same spot on a whole space. Is now a sum traces trace on the fundamental domain. Then the evolution operator is a matrix with element that's a function that you're going to integrate over. So it's going to be sum over H from here, and then there'll be a trace of that matrix, 6 by 6 or 2 by 2 matrix. And as you'll see, you can explicitly construct all the elements for finite groups. It's a subgroup or permutation group. You know how to do this. So this is some number. It's a trace of matrix with zeros and ones. So it's some integer. Could be negative, could be positive, but whatever. And then trace lambda of tilde. So evolution operator that only moves you. This is more explicit. Something where you get a contribution that either you come exactly back, that's periodic orbit and H is identity element, or you progress to another cell that's called a relative periodic orbit. So this integral is a trace on fundamental domain. So this is really a trace of this finite dimensional matrix, which cares about where you started. And this thing has a name, which is the character. So this is character. And then the trace of evolution on the averaged over all group elements. So H goes over all group elements. So that's an average. And if that degenerates, then this number is smaller, because when it's degenerate thing, you only average over one copy, weighted by the character. So this is a symmetry reduced trace formula. So what you have on the left-hand side is you have dynamics in a full state space. And it says the dynamics can be described in terms of dynamics on the symmetry reduced fundamental tile. And remember, that's what we did for 3D system. We started bouncing between three things, and we ended up bouncing in a little triangle, 1/6 of the whole space. And depending on what representation you're interested in, you get different contributions. So this trace becomes sum of traces. Now, the way we get a determinant, we write determinant as e to the trace. So that will become, because it's a sum, it'll become product of determinants. So determinants will become product of determinants, one of each subspace. There'll be this, your eyes might glaze over these characters. That we'll work out some examples and you can work them out. I mean, that's a standard thing you have to do in quantum mechanics anyhow. If you do any solid state physics or chemistry or anything that has 3 particles or more, or even 2 particles, you have to do it. So the good news is there is one representation, which is the so-called fully symmetric representation. So the state in which you look at a function that's averaged over the tiles is equal, weighted and summed up. So before we had symmetric and anti-symmetric, they generalize. There's always one representation which is fully symmetric, and then the other representation. That one happens to have all characters equal to 1. So even if you didn't know your group theory, it turns out you would get, and its dimension is 1, And this is, this average then just becomes 1. And it turns out that for that representation, computation in a full space or computation in a final domain gives you the same trace formula, and therefore gives you the same spectrum. And the fully symmetric space tends to be the lower state. So we're interested in natural measure, the ground state, and the fully symmetric, the ground state is always in that subspace. So in practice, even if you don't know all this group theory, you'll do pretty well, because the thing that you'll compute and the eigenvalue that you'll compute will belong to the most important subspace, the lowest eigenvalue. What the other subspaces do, they have some kind of minus signs here, etc. What it means is that when you look at anti-symmetric subspace, you'll have a function with more nodes. Symmetric one with the flattest. The other one has to have at least 2 nodes because it's anti-symmetric. So they turn out to be states, so that in terms of, if you think in terms of probabilities, it'll mean you have negative and positive probabilities. It's not exactly that way, because whenever you take your density function, you write it as a sum of the coefficients times the eigenfunctions. And the first one is flat. The second one has some coefficient, and it's negative, means you're putting some structure in the distribution. So it doesn't violate probability. But the second one will have to do with decays, etc. And however, these are reducible representations. So if you start in the second space, you will never land in the first space. So you have super selection rules like you have in quantum mechanics. There's some initial conditions from which you'll never see. For example, if you start in fully symmetric initial functions, you'll never see any decays from the other subspaces because they don't belong.